Hello everyone, welcome back to the latest lecture session. So again a very quick recap of what we have been up to, both to let you understand how systems work and how you can predict how systems work, and also obviously to give you what do we say, exams that can get your juices flowing, right? We were talking about mass balance, right? And that context, I guess we looked at the fundamental equation, and then for flow in one particular direction, right, in only x direction, right, where concentration is changing in only one direction and neglecting diffusion, we came up with this particular term, right, plus or minus sources or sinks, right. And here I guess we have rate of formation minus, typically sources or sinks, they are the reactions leading to formation or loss of the relevant compound within your control volume, right. The control volume can be a lake, a river, it can be a city, and so on and so forth. City, when I say city, the atmosphere or such right above the city now. In that context, we have also seen, I believe, the macroscopic equation, right. If I am not mistaken, it's nothing but, I mean, you get this by rearranging this equation. You can see that we take this term to the right hand side, and for macroscopic scale you can get the relevant equation. So this is the accumulation term, it's nothing but what do we say, mass coming in, Qn Cn, volume per time, right, discharge into concentration coming in for the particular compound you are applying the mass balance on, Q out, C out. So this is mass coming out, product of flow going out, and concentration of the compound in the flow going out, plus volume into rate of formation of the compound minus rate of loss of the compound. This is for the macroscopic scale, right. Again, you need to choose the control volume in such a case, in such a way that within your control volume the concentration of the compound that you are choosing is the same, right. And that is one particular aspect. If not, you can always use this particular equation where you also let the concentration change with space, right. And let us move on and see what I have here. So, okay, in the context of different systems, we have some ideal case reactors or systems. So, let us look at what they are. The first one is a batch reactor, and the next one is what I have on the slide, plug flow reactor, and the other one is a continuously stirred tank reactor, or again I repeat, continuously stirred tank reactor or continuously mixed flow reactor, right. Let us just look at, again, these are the ideal case reactors, but for this class we are obviously not going to go into greater detail. Let us look at some of the practical applications. Let us say batch reactor. So, let us say if I take this room, typically indoor pollution, at least in bigger auditoriums and such, is an issue, right, and you need to, let us say, model the particular indoor air pollution within a particular auditorium, let us say, and you can think of it, let us say, as a closed system, no flow going out, no flow no flow coming in, and no flow going out, right. And so, it is a closed system. In that case, obviously you are going to say that, or we are going to call that a batch reactor or a batch system. And let us apply this particular equation to that, or rather both the equations to that particular system. So, what do we see out here? We see V dC by dt, concentration changing with time. Since there is no flow coming in and going out, both these terms are going to be 0. So, I am just going to be left with volume into rate of formation minus rate of loss, right. This is the one for batch reactor. Obviously, you can simplify it further and you can apply it on this equation too, right. Again, dC by dt, change in concentration with time within that space, plus is the concentration changing with distance within that auditorium. We are assuming that it is a homogeneous system. So, no. So, this term is going to be 0 for the batch reactor, right, is equal to the sources or sinks, which in this case are just the reactions that are occurring and affecting the concentration of the compound within the auditorium. So, that is what we have, I guess, right, for a batch reactor. Batch reactor, what else? A lake, depending on the level of homogeneity. Lake is what is it now? Batch reactor, you can say so. So, the next one is what I had on screen. So, let us move on to that particular slide. So, plug flow reactor. In this context, if you remember, we looked at a picture earlier where we had the waste being given out into the stream, let us say, right, and after some time you see that this is the plume and the flow is in this direction. So, let us say this is Haridwar and this is Roorkee. You want to model what the concentration is at Roorkee if a particular compound, let us say A, is being given out at concentration at Ca, let us say, at this point in Haridwar. So, how do I model the system? Because here obviously there are reactions occurring and the concentration will change with time. When I say concentration changing with time, we are not going to look at driving along the Ganga Canal road from Haridwar to Roorkee and taking samples, right, because there you are not keeping the space constant, right. So, if you are doing so, that is going to be something else, we will look at what it is. When you say you are going to measure change in concentration with time, you need to keep the space constant, as in let us say you need to choose just this point, take a sample at 9 a.m., 12 noon, let us say 3 p.m., 6 p.m. and so on and so forth at this particular point in space. So, you are going to look at the change in concentration at that point in space with time. So, right, that is what we have. Right, but here as you see, due to dilution too, right, you have advection too, right, you are going to have dilution too, right, and it is transporting the sample from one point to the other. So, you are also going to have change in concentration with distance too, right. For example, let us say a point at time here, 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 here and so on and so forth, you will have change in concentration with distance. So, how do you capture that? Let us say, can you capture that with your what is this now, macroscopic scale equation? The macroscopic equation was V dC by dt is equal to mass coming in minus mass going out plus sources or sinks within the reactor. As you see in this macroscopic equation, we are assuming that the concentration within the reactor itself is the same, right, but that is not the case in this particular canal, river or such. Let us say you see that concentration is changing with distance. So, how do you capture that? That is the effect due to advection too, right. Advection, what is it now? When you have the mass of the compound being transported due to fluid flow or net fluid flow in one direction, well, you can say that it is advection now, right. So, that for that obviously you can what do we say, play around with this equation and get to the relevant equation that you want that will suit this particular control volume, or we can use the fundamental equation that we discussed earlier, dC by dt plus u dC by dx is equal to rate of formation minus rate of loss. So, x, right, distance in this direction, by u is constant here, the velocity. So, x is what now? X is distance, which is a variable, keep that in mind, by distance per what is this, time, I guess, right. So, in effect you will get time, but this is not a constant value because this distance is changing. So, x by u we call it to be the hydraulic retention time, hydraulic retention time, hydraulic retention time. So, it is going to give you an idea about how much time is your particular compound spending within the reactor, right, hydraulic retention time. So, that is what we have, theta equal to x by u. So, my equation will now be dC by dt plus dC by d theta is equal to rate of formation minus rate of loss, right. So, this is at non-steady state condition. So, obviously at steady state, this equation will obviously just become dC by d theta is equal to rate of formation minus rate of loss, right. Again, theta is not approximation, will give you an idea about the time that your water molecule or compound will spend within the reactor. Again, how do you calculate it? It x by u, I guess, right, x in this direction, right. So, if it is 0 out here and this is total length L, let us say, right, 0 to L. So again, you can look at the similarity with the equation derived for the batch reactor, dC by dt equal to rate of formation minus rate of loss, but again keep in mind that this is the case for steady state. So let me see what else I have here. Looks like I was just discussing this. So again, I have CSTR or completely mixed flow reactor. So looks like here I have the full form. So again, as I mentioned earlier, this can be the approximation for a lake, right? Typical example is a lake, but again depends on the size of the lake and such, but you know, over a considerable period of time, more or less CSTRs, yes, you can use that to model a lake. So you have mass coming in and mass going out, and this symbol, that is the reason I use this is continuously stirred, I guess, right. So continuous stirring meaning the concentration of the compound within this reactor is constant or the same, right. It is not changing with space inside this control volume. This is my control volume. So obviously I can apply the what is this now, macroscopic equation. V dC by dt is equal to mass coming in minus mass going out plus volume into rate of formation minus rate of loss, right. So from here you can calculate whatever it is you need. So if it's at steady state, this term will be 0, concentration or no variable will change with time. So concentration also will not change with time. So then you will just be left with this, and you can play around with this equation to get whatever it is that you are trying to calculate or model, let us say, right. So I believe we have looked at the three what do we say, types of reactors, right. So let us move on to the next aspect here. So here we have a few problems obviously to what do we say, help you understand further with respect to the applications of mass balance. A cooling tower is operating at steady state and water is lost as water vapor in evaporation. Okay, here I guess it is evaporative cooling, right. That is what even our body tries to do, I guess. When you run, your body heats up, right, and how does your body try to cool down? Again you sweat, and then the sweat evaporates by taking the heat from the body, again evaporative cooling, let us say, right. So that is the same principle here that is used in cooling towers now, right. With respect to the thermal power plants and other plants, let us say, where you need to expend energy. So earlier you had to, let us say, for example in Vijayawada or such, you had this barrage, okay, where you had to impound water up to 12 feet and downstream just limited flow, let us say 0.5 feet or none at all usually. And here 12 feet was for two purposes. The Vijayawada city is somewhere out here downstream, one to supply water there, and more importantly because they had a thermal power station here. So their cooling towers were different, so they needed continuous, what do we say, source of water, right, and water used to cool and the hot water used to come back here, right. So continuous flow of water was required, and for that a certain level of water was required. But obviously with this evaporative cooling towers, you do not really need such a continuous flow of water. Again, let us that is just what do we say, some trivia, I guess. So what we have here, this is the cooling tower. Water is lost as water vapor in the evaporation stream and small droplets of liquid in the drift stream. So you have drift and evaporation, right. That is obviously always going to be the case when the water vapor is evaporating, right. You obviously are going to have loss of some water too along with drift, or in the form of drift rather. And water is, whenever required, typically we add water in the form of makeup, right, when required. Why is it? Obviously because water is being lost, right, and it is removed in the blow down stream, right. Whenever certain variables are too high, you try to bleed the water, so that is blow down, I guess, right. Total dissolved solids include all the compounds that remain in a test after the water is evaporated. So that is a key aspect. Yeah, total dissolved solids, right. You are going to evaporate the water, and whatever is residue is left, that is the total dissolved solids, right. So assume that drift and the recirculating water contains, drift and the recirculating water contain, where am I, contain the same concentration of TDS as does the blow down. So whatever is in the blow down is the same as that in the drift and in this recirculating water, let us see, right. So you the heat exchanger, hot air comes in, not air, water comes in. Now here it cools down and again is what do we say, sent back to the heat exchanger, takes up heat and again loss of heat and so on and so forth, right. So, that is what we have out here, a cooling tower. So, assume that drift and the recirculating water contains the same concentration of TDS, okay, we are done with that. Right, what else? Assume that the TDS is not destroyed or produced in the system, that is obvious. Typically we are talking about inert what do we say, compounds here. So, the first question is, if the makeup volumetric flow, if this flow is 2 into 10 power minus 3 meter cube per second, what is the concentration of TDS in the blow down or the recirculating water? In the blow down, what is the TDS, concentration of the TDS, what is that, right. And what are some of the values that we have? We have that concentration of TDS in makeup to be 500, evaporation flow is given, drift flow is given, right. So, first aspect is mass balance on, let us say, water. So, here it is just nothing but what is it now, Q or flow coming in. So, this is my control volume, let me erase all this content. So, this is my control volume. By choosing the control volume in this manner, I now do not need to consider the recirculating flow. I am only now considering the relevant variables about which I have some information, let us say, and or those variables which I need to calculate. I am not concerned about recirculating flow or what is happening within the control volume, right. So, now what do I have? I have Q makeup, and that is obviously going to be equal to, again, mass balance here, right, on water, if I can say so, is going to be equal to all the flows going out, Q evaporation plus Q drift plus Q blow down, let us say, right. And I have Q makeup, Q evaporation and Q drift, drift flow, evaporation flow and makeup flow. So, from that I can calculate the blow down, obviously, right. And here though the question is that what is this now? The concentration of TDS in the blow down and recirculating water, what is that, right. So, obviously now the variable of interest is TDS. So, I am going to apply the mass balance on TDS. So, again it is pretty simple here, mass coming in has because again the system is at steady state, it goes without saying if it is not been mentioned, okay, at steady state I guess it has been mentioned. So, right, you can look at the macroscopic what do we say, scale equation for the CSTR, let us say, no reactions here, right, and it is at steady state. So, what will that more or less turn out to be? Q in C in is equal to Q out C out, right. So, here Q in is Q makeup into concentration of TDS in makeup is equal to Q evaporation, concentration of TDS in the evaporation flow or in the evaporation, let us say, and concentration or flow rate of drift plus concentration of TDS in the drift plus Q blow down into concentration of TDS in the blow down, let us see. But one key aspect here is that, as we discussed earlier or as the information provided informs us, TDS includes or TDS is measured by, how now? You are going to evaporate the water. So, whatever is left is the TDS. So, in this evaporation there is not going to be any TDS, right. So, this concentration evaporation term is 0. So, this is going to be 0. So, now let us see if we can calculate what we want. So, Q makeup we have that, C makeup we have that, QD, QB we have that, and C drift and C blow down are the same. I believe that is what was mentioned. Assume that the drift and the recirculating water contains the same concentration of TDS as the blow down. So, one equation and now one unknown, and I can solve for CD or CB, which are both the same, right. And again just another example or such, I guess, right. So, let us see what we have. So, steady state conservative balance around what do we say, on water around the tower, this is what I discussed. So, what do we end up with? 9 into 10 power minus 4, again E minus 4, this is the nomenclature we use in Microsoft Excel, that is why this again E is not exponential, it is capital E here, it is 9 into 10 power minus 4 meter cube per second. So, that is the Q blow down, right. And steady state conservative balance over TDS, it is nothing but Q in C in is equal to Q out C out, and so I am now going to be able to calculate the concentration of TDS in the recirculating water. So, that seems to be 1000 milligram per liter. So, part B, I guess, what is question or what is part B? what would be the minimum possible makeup flow, and what would be the concentration of TDS in the blow down or the recirculating water if at that makeup flow. So, we will look at why we need to have blow down in these evaporating towers, but that is later. But again, as you see, you can never rule out evaporation, you can't rule out drift, right, that is the whole purpose of a cooling tower. But you can stop blow down. So, the minimum will be equal to, or makeup flow will be equal to the loss of water due to evaporation and drift. So, the Q minimum will be equal to Q evaporation plus Q drift, or when Q blow down is 0. But then obviously what is going to happen, think of this. So, you have water at a certain TDS coming in, right, and over time let us say you are having loss of what do we say, water, but the TDS is now going to get concentrated in the system, because is the water loss via what do we say, water vapor going to also remove TDS? No, it is not going to remove TDS. So, the TDS is building up inside the system. So, what would you expect if you have no blow down from time to time, right? So, you are going to expect that the TDS within the system is going to increase. So, here what is the TDS in the makeup flow? Let us calculate that. So, we have what is this, Q minimum is Q evaporation plus Q drift 1.1 into 10 power minus 3 meter cube per second. And then again applying similar mass balance as here, right, but here we say that the blow down is 0. Yes, I guess this is what I have, maybe I have minor error there, you can calculate, clear that up yourself. So, looks like the TDS in the blow down or the recirculating water here is 5500. Compare that with what the TDS is in the recirculating water from part A when we had Q blow down, and here Q blow down is equal to 0, here Q blow down is not equal to 0. So, obviously, you see the need for bleeding the water from time to time from the recirculating flow within the cooling tower. If not, you will have increasing TDS, or with respect to hardness, that is what we saw earlier, you know, you will have scale formation on the heat exchanger, right, and that is obviously going to what do we say, lead to huge what do we say, maintenance losses, let us say, right. So, that is something to keep in mind. Again, some of the aspects we have learned with respect to hardness and mass balance out here, right. So, let us move on to the next aspect. Let us see what question if any I have. So, I guess here we have, or we are going to derive rather, the steady state phosphorus concentration in a lake with the following conditions, right. Okay, so, why phosphorus? We are going to look at that later, but again humans need obviously source of carbon for carbohydrates, proteins, nitrogen, and again phosphorus, let us say, right. These are the nutrients that we typically need every day. There are other micronutrients too. Again, because we need them, that also means that, typically means that other life forms also need them. So, when you have an excess of these what do we say, nutrients and carbon in lakes or such, you are going to have algal growth, considerable algal growth and exponential algal growth, leading to an explosive growth as I mentioned, and algal bloom, I guess. That is going to lead to, you know, decay of algae after some time when there is no more nitrogen or phosphorus, or enough nitrogen or phosphorus, then your algae is going to die. The dead algae, the microbes are going to feed on them, and then obviously your dissolved oxygen is going to come down greatly, and your size of the lake will also decrease over time, let us say, right. Again, that is what happens in considerable Indian lakes, at least in the villages, because of excessive use of fertilizers. These fertilizers, whenever you have runoff or such, are now coming into the village lakes and leading to algal bloom. So, lakes which were now this size, slowly but surely they are being affected and their size is getting reduced, let us say, or is reducing. So, what do we have? We are going to try to calculate the steady state phosphorus concentration in the lake. So, the phosphorus removal rate or settling rate is Vs. So, let us understand the system. Looks like we have a lake here, top view, side view, okay, and we have Q in, C in, and Q out, C out, and looks like we also have an industry dumping phosphorus directly, but the units are different here, grams per second, and the area of the lake is given as A, but again we are taking quite a few assumptions here. Concentration of the compound in the lake is C, and also as I mentioned here, you know, your phosphorus can absorb or can settle to the bottom depending on the state or form it is in. So, it is settling to the bottom too, okay. Physical removal here. So, there are different sources and things. So, firstly, what is the kind of reactor that we need to what do we say consider? Can it be a batch reactor? No, because you have flow coming in and flow going out. So, it is not a closed system. So, it can be an open system which can be either a plug flow reactor or a continuously stirred tank reactor. Plug flow reactor, you have change in concentration of the compound within that reactor, let us say. So, here is the concentration changing within the lake though? No, it is not. So, it is not plug flow, let us say, right. So, it is going to be a CSTR, continuously stirred. Here obviously we are assuming that the concentration of the compound within the lake is same because it is relatively homogeneous, let us say, right. So, that is what we are assuming, and that is why we end up with CSTR. So, what is the equation for your CSTR? We know that V dC by dt, macroscopic scale equation, is equal to mass coming in minus mass going out plus any reactions or such that we have that can be leading to loss of the compound. But here I guess we are not having any particular reactions, but we do have a source here and a sink here. A source is the direct what do we say input of your phosphorus, but let us see if the units make sense. Units here are volume into concentration is mass per volume into time, volume cancel out. So, the units of each of these variables will be mass per time, and here we do have it in grams per second. So, we are on the right track. So, minus the sink has to be this. So, settling rate, phosphorus is settling to the bottom and it is being removed at the rate of some meters per second. So, I have meters per second, let us say, right, but I need it in terms of mass per time here. So, obviously, I need to bring in my multiply it with my concentration and also with respect to my area of the lake, let us see, right, top view area of the lake. So, here volume per time, mass per volume, so mass per time. So, looks like we are on the right track, right. So, obviously, here they say that it has to be steady state. So, if it is steady state, this term is going to be 0. At steady state, no variable will change with time, right. And so, now you have Q in here. So, Q in and Q out are the same. If not, obviously, the volume of the reactor will change, right. So, that is something to keep in mind here, right. So, again here we have Q in and Q out to be the same. So, I will just use the term Q. Q into concentration of the compound coming in 0 is equal to minus Q same as Q in, C out here, right, C out plus the source minus Vs A C. C is the concentration of the compound within the lake, but here we do not know C out, we do not know C. We can have S, we can have Vs, A, Q and so on and so forth, Q and so, but we only have one equation, two unknowns, how do we solve it? But the key here is that it is a CSTR, right, continuously stirred tank reactor. So, whatever is in the lake, what we are assuming that it is homogeneous, and so the concentration of the compound leaving the reactor will be the same as the concentration of the compound inside the reactor though. So, C out and C are the same, right. So, with that you can simplify and get the relevant variable C, I guess, C or C out, right. So, I guess with that I am almost out of time. Again, as I mentioned, we want you to be relatively more knowledgeable in different aspects, and I guess with that I will end my session, and thank you for your patience.